So there are a couple of equations that we're going to use when analyzing shock waves, and they're actually pretty easy to derive. So let's look at a picture that we've seen before. Here we have an object moving faster than the speed of sound, and so that creates this shock wave here. So this ring here is the most recent sound wave emitted, and then this is the first sound wave emitted, so it's had the longest time to spread out. We're showing them as rings. They're actually spheres, but it's harder to visualize that. If it was traveling slower than sound, all of the smaller rings would be inside the larger ring, but when you go faster, then this can happen. And if we imagine this guy spreading out, this leading edge here that becomes part of the shock wave, that is moving out in a direction perpendicular to the plane of that shock wave. I don't know why my perpendicular like to disappear. So we can derive this equation here, where we can find the angle theta, which we define as not the entire width of the cone, but just half the width of the cone, or the angle between the motion of the object and the shock wave. So that ends up just being the ratio of speed of sound to the speed of the object, which we can see really easily here. These distances are over the same amount of time, so these are also, you can have a triangle here of the relative velocities. So this side of our triangle here represents the velocity of the object. This side of the triangle here represents the velocity of sound, because that's what's propagating out here. And so if that's theta and this is theta as well, then it's obviously the sign is just going to be opposite over hypotenuse, which gives us our nice equation here. Okay, one other equation that we're going to look at deals with what are called Mach numbers. You've probably heard of this airplane can fly Mach 3 or whatever. And what a Mach number is, and it's named after Ernst Mach, the same guy who had Mach's bucket and that we talked about on the first day of school, and with the universe spinning around the bucket and all of that stuff. Same guy. Anyway, a Mach number is simply multiples of the speed of sound. So if you're going Mach 2, that means you're going twice the speed of sound. Mach 3, you're going 3 times, and so forth. So to calculate that, you take the speed of the object and you divide it by the speed of sound. Simple enough. Since that is our Mach number, and this is the equation we had for the angle of our shock wave, you can tell that those are just inverses of each other. So this equation here is also going to come in handy sometimes when you don't know either of these things, but you do know the Mach number. You could still find the angle of the shock wave. Alright, let's apply a few of these wonderful equations. So here we've got an airplane flying at 725 meters per second at an altitude where the speed of sound is 290 meters per second. So we mentioned that the speed of sound changes with temperature. It also changes with pressure, and when the air is thinner, sound travels a bit more slowly. And when you're finding the Mach number or doing calculations of the angle of the shock wave, you don't just always use 343. You need the speed of sound at the location where the shock wave is being produced. So our Mach number, again, the equation is just the ratio of the speed of the object, in this case the airplane, over the speed of sound at that location. So that's just going to be 725, and if we want to throw our units on there, we can, over 290 meters per second. You'll see the units cancel out, so Mach numbers are just numbers without units. This works out to be a nice 2.5. Ooh, imagine that. Maybe I made it up that way. Okay, so pretty easy there. Next part, what is the angle of the shock wave? What is the angle that it makes with the direction of the airplane's motion? So airplane moving this way, shock wave looks like this. We're trying to find this angle theta here. Our equation there was sine theta equals speed of sound over speed of object. Or another way we can write this as the inverse of the Mach number. So we're going to have theta equals the inverse sine of 1 over the Mach number. So we can just plug that puppy into our calculator, and we find an angle of approximately 23.6 degrees. So a lot of these calculations aren't too tricky. Let's look at one that's not too bad but has a number of steps in it. So here we observe a plane flying straight above us. somehow we know that it's traveling at Mach 1.7, and we want to know how long after the plane is directly above a person will they hear the sonic boom. So let's make a little diagram here. So 6,400 meters up, you have some person standing here. The airplane flies over, and there's a shock wave coming, trailing behind the airplane at some angle theta. And it's when this shock wave hits the person's ears that they hear the sonic boom. So if we know the Mach number, we can find theta, because it is just the inverse sine of 1 over the Mach number. So that gives us theta is about 36 degrees. Okay, so that's the first piece to our puzzle. Now we essentially need to find the time it takes the airplane to travel from this location to this location, and that will tell us, that will also be the time for the shock wave to get to this location here. So we want to find this distance, and it's going to be the velocity of the airplane, we could say velocity of object, times time. Well, we don't know that quite yet, but we can find the distance because we have this side of our triangle and we've got our angle. So we can use tangent of 36 equals opposite over adjacent, so 6,400 over the distance that we're trying to find. Rearrange this, and the distance is 6,400 over the tangent of 36, and that works out not nearly as nicely as some of our previous answers. 8.5 and on, but that's enough for now. Okay, so that gives us the distance, which is good, but we want to find the time. And in order to get that, we also need to know the velocity of the object. So we have to dig deeper. Well, we've got the speed of sound here, and we've got the Mach number there. So that will allow us to find the velocity of the object, because the Mach number is equal to the velocity of the object over the velocity of sound. Now, technically, the speed of sound is going to change over this altitude, but we'll just imagine that it's constant, or say that's the average speed of sound throughout that change of altitude. So if we plug in here, we've got 1.7 equals speed of the object, which is what we're going to try to find in this little step. Plug in the speed of sound, it's 300. Rearrange that guy, and we can solve for the velocity of the object. 300 times 1.7, which works out to be 510. So now we're just about there. We can plug into this d equals vt guy, where we've got the distance 8798.5. We've got the velocity of 510, and now we can solve for time, which works out to be 17.3 seconds. So that's how long after they look directly up and see the plane directly above them will they hear that sonic boom pass over them. Okay, see you next time.